Welcome to a lesson with Dr. Powell. Let's take a look at a fascinating idea that if you take a matrix like this, it has two columns and it's transposed right here, you multiply them together this way, you can multiply them together that way, um, and you compare, you get a square matrix in both cases, but compare their characteristic polynomials. It's kind of fascinating. They're the same, but this one's just x multiplied to that one. There's a few different consequences of this, and one of which is calculating area. I'll just kind of forward ahead. Think about those two column vectors in the matrix B, 1, 1, 1, and 2, 3, 4, as vectors outlining a parallelogram. Well, what we're going to actually see is a way of computing the area of this parallelogram the same way as you might compute a length of a line. You project the line onto different axes, you square those, add them up, and square root. Well, take this area and project it onto different axes, one at a time, or not just axes, actually, um, planes, the XY plane, the ZX plane, the YZ. See what the projected areas are, square those, add them up, take a square root, we find area. Kind of a fascinating idea, and that's kind of an idea that we're going to be looking at a little bit as we go along here. So first of all, notice how we could get this 6 is different. Right here, the way we get this 6 is by a determinant. The way we get this 6 right here is the x as the x coefficient is from doing this idea of like getting crossing out one position, looking at a determinant here, this position looking at the determinant kitty corner to it, that position looking at determinant kitty corner. They're kind of all these matrices are kind of centralized on the main diagonal here that we're looking at, all these 2 by 2s. There's 3 of them that we look at. How do we get those? How do we get those? They actually come from this multiplication, thinking of blocking. These two guys with those two guys actually give us this part right here. 1, 2, and 1, 4, 1, 2, and 1, 4 together give us the 5, 9, 9, 17. Think of multiplying that. That's how we get those numbers right here. The 1, 3, so the 1, 3, 1, 4, and the last two and those two actually give us the bottom part right here multiplied together. And precisely what I'm looking at is I'm actually looking at the projections on the different planes, like the x, y, or the x and z, or the y and z. I'm looking at the different projections one at a time in computing these different determinants, kitty corner, that actually add together to give me that coefficient, which is equal to this, which is the determinant of this guy. All right. Now, this guy, in a sense, you can actually think of this area as actually being the square root of this determinant being kind of like the square of that. So it's kind of like, so we can kind of see that relationship as we go along. Here's a little depiction of what's happening. We're looking at the determinant of 1, 2, 3 times the determinant of 1, 2, 3 transpose. Oh my goodness, see 1, 2, 3. So like, it's like we're double dipping on the determinant because we're multiplying this by itself by the transpose of it. But determinants are multiplicative. They pass through multiplication nicely. And the determinant of a transpose is the same as the determinant of the matrix itself. So we get a square on those guys, just as we were thinking. Okay, so here's a question to make this work right, because that's what we're looking at, the characteristic polynomial of BBT or BTB. How are they so nicely coordinated? Are they always that way? Well, let's take a look at a little proof description. Okay, so let's suppose that B is an n by k matrix. That means it has n rows and k columns. You can fill it out in blocks. Think of this as being a block of zeros, and this is a matrix B right here. Okay, and filling out to an n by n matrix, M. So it's a square matrix. Now we can compute MTM and M and MT by some different blocking. This we actually get the bigger matrix by, and for this one we get the smaller matrix with zeros right around here. Okay, now let's take a look at M itself, and let's put it in Smith normal form by doing row operations and column operations to get us this. Let's reuse these matrices, this row operations matrix and that column operation matrix, and we can we're going to be using them also on the matrix MT, but kind of in a funny way. We'll put the C inverse on this side, the R inverse on that side, and we're going to get some matrix, whatever it is. We don't know what it is, but by block multiplication, we can kind of think about it in blocks similar to the blocks we have here. So we'll kind of keep that in mind. Okay, but M we can solve for, get R inverse, this guy, C inverse. Okay, next, taking a look at MT, which is equal to this, we're going to multiply these together in different ways. We multiply them this way, we get this matrix. We multiply them that way, we get that matrix. Couple notes on this. First, see this DE00 and DF00. These should have the same characteristic polynomial in and of themselves. Because if you think about putting x's down the diagonal, you can have x's here, and anything that happens over here really doesn't have anything to coordinate. It's always kind of to zero. This f doesn't do anything. This e doesn't do anything. Really, the only thing that matters, even if you're doing a cofactor expansion, you can kind of cofactor expansion, you can kind of see this. If you're just using the single x here, you can kind of go down to what's kitty corner x, kitty corner, kitty corner. You go all the way kitty corner until you get down to d. E doesn't mean anything. Same thing here. Kitty corner until you get down to at d if you're doing cofactor expansion. So really, these have the exact same characteristic polynomial. That's number one. Number two, if you take since determinants are multiplicative in nature here, and if we have, if we're thinking about matrices that have polynomial entries in X, if you take a matrix and its inverse on the other side right here, I mean, that's not going to affect the overall determinant of this guy at all. So it's going to be the same. And if you distribute these guys in, these P and P inverse cancel over here, and we're left with this. But wait a minute, these are the same. These guys have the same determinant, which means you have the same characteristic polynomial for A, because this has the same determinant as xi minus A. Same characteristic polynomial for A as well as this. Okay, where we have like P, A, P inverse. Sometimes this is called A is similar to this matrix. I mean, this is kind of like change of base for A. You have a matrix and its inverse on the other side. Changing its base does not change the characteristic polynomial. So if two matrices are similar to each other, meaning that they're just a change of base away from each other, sometimes noted like this, if two things are the same, but they have the same characteristic polynomial. Okay, so using that idea, characteristic polynomial, and that this has the same as that one, characteristic polynomial doesn't change from here to here, which means that this guy has the same characteristic polynomial as that guy. All right, so this guy has the same characteristics as this one, and this one is just a power of x away from that one. So we do have the nice coordination always. Well, this is really nice because this tells us to get that area, if we're thinking of it as square root of squares, a sum of squares of projections, we can actually get that right in here by examining the determinant of this guy, because that'll actually coordinate with the sum that we were taking and looking at over here. So going back, this really does have a nice coordination, and we really can just simply compute this determinant and take a square root and end up finding the area of that parallelogram that we were looking at right there. So let's take a look and make sure that in making this consideration, let's see, the determinant of this, remember, was right here. That's 6. So the area of that parallelogram then would be the square root of this. So the square root of 6, to finish this off, is the area of that parallelogram. Thanks for watching.